To really learn the Born-Haber cycle, you have to have clear all of the definitions. There are some that you've learned already in AS chemistry, and some others that are a bit more complex and you come across here. Here is a little summary, and what I would suggest you to do is look in your book and try to get some equations down so that you understand each of these definitions more. But I will move on directly to the Born-Haber cycle because I think you will see how we will apply all of these definitions for this. So let's build it up. For this reaction, you may recognize it from the definitions that we have two elements making up a compound. This is the enthalpy of formation. Anyway, the point of the Born-Haber cycle is that we take this equation, like written as a reactant to product, and we put it vertically, where the arrow actually has a meaning. In fact, the arrow means that it's exothermic if it's going down, like in this case, or endothermic if the arrow is going up. Okay, so you needed to kind of visualize. Sometimes you're given the list of the equations in the exam, and therefore you have to rearrange things. So think it in this way, like, oh, I have to rearrange it in a way that the arrow going down means exothermic. The arrow going up means endothermic, energy taken in, because the Born-Haber cycle at the end, that the vertical axis is kind of like a change in energy. Keep this in mind when I show you some numbers. But let's continue. Do you remember the ABC cycle? If not, here it's time to revise Hess's law, and maybe you can have a look at my lessons on the enthalpy, because these cycles can help us working out an equation to calculate the enthalpy of our reaction. Let's say A and B is the reaction that we don't know the value of. C, in the case of this first reaction, is a common product, is a common reactant in the second cycle, and here is just an intermediate. But I don't want to bother with this if you remember from AS chemistry. Otherwise, I will put the link up there to the other lesson. But it's important that in the Born-Haber cycle, you can recognize this ABC. Once again, it's because one of these steps, you will have to find the value while having all of the others values. So notice how we just not the triangle that we had before. Now the shape is a little bit different. Notice the similarities to simplify it. Let's build it up. So the first step, so in here, I want you to notice, okay, I know we got a bit more complex already, but let's break it down. We have the enthalpy of formation. That was the first step. Everything will lead to this enthalpy. I'm going to say the definition is the enthalpy change when 1 mole of ionic lattice is formed from its gaseous ions. This is lattice enthalpy. So we want to get from the enthalpy of formation to the lattice enthalpy. The difference between these two is we have the standard element and we have gaseous ions, which means that to get to the gaseous ion, we have to go through several steps. If it's a solid, it has to turn into a gas. If it's a molecule, it has to turn into an atom, and then the respective ions. In fact, after this enthalpy of formation, we put the enthalpy of atomization. So the enthalpy of atomization, as the name says, atom, so what it could mean, is the enthalpy change when 1 mole of atom is formed from its element. So 1 mole of atom is formed, okay? So the enthalpy change of atomization, if we have a solid to a gas, it's also called sublimation. But if we have a molecule, it turns into an atom. Notice how this would be true enthalpy change of atomization, because if we break down the whole diatomic molecule, we're left with 2 atoms. Keep that in mind for more complex cycles when you have more than 1 atom involved. So the change is, notice also what's changing is 1 step at a time. Yeah, each step is 1 reaction, solid to gas, the atomic molecule to atom. So what do we have next? We have the gaseous atom. Well, we needed to finish it with the ions. In fact, the next step would be the ionization energy and the electron affinity. So the ionization energy is, as we said from the definitions, the enthalpy change when 1 mole of electron is lost from 1 mole of gaseous atom to form 1 mole of gaseous ion. Here you can build up the definition as you want, as long as you include the key points. So enthalpy change of ionization, in this case of A. The opposite of it is electron affinity, which is the enthalpy to gain 1 mole of electron. In fact, notice how this electron is lost from A, and in the second step, it's gained by B. So the electrons have to be included in each step. Notice also the electron affinity is exothermic. Now, we've done all of the changes to get from the element to the gaseous ion. This is important because now we can finally calculate the lattice enthalpy. It's common that in a question you're given calculate the lattice enthalpy, or if it's more complex, you could be asked to calculate the enthalpy of atomization or the electron affinity or any other. But using this ABC cycle, so that instead of going in the direct route A to B, you look at the indirect route, we go the other way around, you can calculate any of these enthalpies. So I always like 2 methods here. Maybe you remember the simple equation where the simple equation is that the enthalpy of formation is the sum of all the other enthalpies. That's pretty straightforward, and you might even remember it, which means that then you can rearrange it to find whatever you're looking for. But if you don't remember it and you have to work it out, just use the ABC cycle. So the indirect route, remember, opposite direction, we change sign. Same direction, we keep the same sign as it was. Okay? So 2 alternatives of calculating. And very often the point is to find the lattice enthalpy. That's why I would just try to with the examples that you do, try to follow this indirect route and see if you understand what I mean by changing the sign or having the same sign. Okay. Now there is a bit more complex one, and this is from exam papers, just the table with the values. Notice that here you're given just the name, so you need to be able to translate that into equation. Very important. But sometimes, for example, oxygen is a 2- ion, so it's going to have 2 electron affinities. So it's going to be another step. I also want you to notice something. The electron affinity of oxygen, the second, it's positive. The first one, it's negative. So you need to remember that in building the cycle, one will go down, while the second electron affinity will spike up, then to go down to lattice enthalpy. Can you visualize it, looking at having this fresh in mind, the cycle that we just did? That's important. And then, well, the ratios are super important. Think about it. We have potassium and we have oxide. What's the formula of potassium oxide? 2 potassium for 1 oxygen. So the atomization and the ionization energy of potassium will have to be times by 2. So with all of these tips, I hope you can try to build up the cycle. Yeah, comment below if you want any help. Another part, if we have a positive ion that has like a 2+ charge, as we know, the ionization energies are successive, which means that there's going to be another number here, first and second electron affinity, ionization energy. Okay, so as you can see, the second is a lot higher. So a very common question that you will get is, explain why the second ionization energy is more endothermic than the first. Okay, and of course, another very common question, explain why the second electron affinity is endothermic while the first is exothermic. So for the trends in ionization energy, you should remember from periodicity topic or the atomic structure topic. So make sure you go and revise that. But always think about the attraction between the electrons and the nucleus. So what is that? The nuclear attraction. So in sense of, for the ionization energy, we know that removing 1 electron decreases the ionic radius because now the electrons are more attracted to the nucleus, so more energy is required to remove the second electron. So always try to put into your explanation attraction or repulsion, okay, nuclear attraction. So those are some of the keywords. In fact, for the electron affinity, think about it. Why is the second one endothermic? For the repulsion, because oxygen. In the first electron affinity gains 1 electron, so it's oxygen minus, but then to get a 2 minus, you will have to overcome the repulsion, yeah, of the electrons, okay? So you can see easy marks, and you can stick to the very, very simple, concise definition. So other very common questions are about the lattice enthalpy, to know if it's exothermic or endothermic, comparing the energy of the lattice enthalpy. You have to explain why. Just remarks in this case, but the concept can be a little bit tricky. That's why I'm including the link in this presentation, but also I will add it in the in the YouTube video here, to go and check to understand better the charge density, so that you will be able to answer this question about the difference in lattice enthalpy. So with this brief explanation of the Born-Haber cycle, I believe that you can now try to construct your cycles. So if you don't have examples in hand, please take a screenshot of these two slides, and construct your own cycle. Do that by focusing on the definitions, as I was saying before, because the definition can translate into the equations, and the equation can translate into the definition, so that you can construct the cycle with ease. Okay? Comment if you need any help, and I hope you enjoyed the lesson.